This is the project for group 3. We were given petrophysics. Task 1, we had data input, unit conversion, average calculations, where we basically were given experimental data, which we put into our script, and we asked the user to correct data which was outside of the ranges that we needed. We also calculated a few values which were used later on in task 2, which was Darcy's law equation and permeability. In this task, we created a function to calculate permeability from Darcy's law, which was given here. We solved for K. In task 3, which was error calculations and graphs, we were told to calculate many different values in order to calculate the percentage error in measurement, and then we created a chart that shows the relationship between permeability and flow rate setting, and we also plotted for average flow rate versus average delta P, and we created a trend line for that plot. Task 1 in more detail, we were given a data set for maximum pressure, minimum pressure, and time for flow rate settings, and we were told to correct the data, ask the user to correct the data that fell outside these ranges and to correct them to these pressures and times. And then if the user tried to correct the data more than 3 times, we'd terminate the program and display an error message. And we also had to calculate a few different values that we would use later on for Darcy's law equation. Our code, after the basic housekeeping commands, we just inputted the data. We decided to input the maximum pressure, the minimum pressure, and the time all together because we decided that would be more efficient than just having each max pressure, min pressure, and time for each flow rate settings. This command finds the position of every value in the maximum pressure that's greater than 75 and puts them into column vectors, the position for each row and column. If these vectors didn't equal 0, then that meant that at least one maximum pressure reading was greater than 75, because if this found nothing, then these would be equal to 0. M, we made it equal to the very maximum pressure that was the maximum value in that entire matrix, and then X we use as sort of a counter. For our loop, while M is greater than 75 is our while loop. While the very maximum pressure in this matrix is greater than 75, then we need to run the loop and ask the user to replace the value. So we just ask the user here, and then we replace the value in the position that we found over here of the row and the column, and we used X, the position, the first position of these column vectors, and then as the loop ran, we added X to 1, so the first time the loop ran, it would replace the first position, the second time it would replace the second position, and so on. And then here we replace M so that this would be updated to the new pressure in the matrix, because obviously it's been changed after the user has inputted his change. And then we have this if statement. If the loop is ran more than 3 times, then we have a error that's displayed. We did a very similar thing for the minimum pressure here. We just changed the loop to the minimum is less than 35, which is the data that we needed. And then we asked them to replace. We did the same thing for X, and then changed the minimum, the same thing for the if statement. Here it's also the same for time, except it's greater than 165, and it's a different matrix. And then same thing for the minimum time is less than 65. We had to change the value of the pressures from PSI to atmospheres, so we have the conversion rate here, and then we just multiplied every value in the matrix. For the delta P, we just subtracted the 2 matrices. This command is used later on. This is the average delta P. This is just finding the average of the values in that matrix, and then this is the average time, which is the same thing as here, just using a different matrix. Volume was given to us, and here we just calculated the average flow rate. That was pretty much all of task 1. Task 2, we had to create a function for Darcy's law equation. Here's the function. We had to solve for a K, which was permeability. So these dynamic viscosity and diameter values were given to us, and then we calculated area using the diameter. Delta length was given to us, 2.5 centimeters, and then we just inputted the data into K. Our outputs were K and average K. K was going to be a row vector for each flow rate setting, so that there would be an average K for each flow rate setting, and then average K was just the average of all of those, so we just used the mean function that was already in MATLAB, and the average flow rate and the average delta P were our inputs. Task 3, we had to create a function to find the resolution uncertainty, the standard uncertainty, and the combined uncertainty for both time and pressure. So that's our output, and our inputs are the matrix for time, average time, delta P, and average delta P, and then the size of the columns, which we found in those commands. Up here, here is the equations. Time and pressure were both given to us here in the actual project, and all the equations were given to us, so we just plugged in what we needed to. For standard uncertainty, we just did it for each individual column for the matrix, and then we combined it into a vector here for standard uncertainty for time. Did the same thing, except we used the pressure, and then we combined it here into a vector, and then the combined uncertainty used both these values, and it was an equation that was given to us as well. Then we had to find the percentage error, so we needed 4 outputs for that, which represented these 4 equations. We had to input the matrix for average time, average delta P, combined uncertainty for pressure and time, and then the volume and the permeability that we found from Darcy's. We calculated it here. These values were given to us. These were just an equation that were given to us. This corresponds with this equation, and these calculations correspond to this equation. And then we created a vector so that it was one value and one average for every single flow rate setting. And then we combined it here for the final error propagation, and then we calculated the percent error from that error propagation. Then we moved on to find the average error percent overall, so we just used the mean function again. These graphs, this is the first one, which was the bar graph. We just plotted flow compared to permeability. We used these axis limits, and we used the bar function, and we just labeled it, had a title, and then we paused before graph 2. Graph 2 was the average flow compared to the average delta P. And then we had the axis limits, we turned on the grid, and then the X and Y label and the title, just the standard stuff for every single graph and chart. Here we did polyfit, which was needed for the trend line, and here's the trend line equation, and then here's our outputs. That's pretty much the entire project's task 1, 2, and 3. So here the command window, you can see it's asking you to replace it, and we're supposed to replace it with 73, and then 37, and 37, and then 164.9 and 65.2. And so we get the first figure and then the second figure for each flow setting. Permeability K and error percent are this and this respectively, and it just repeats it for each flow rate settings, and then it gives you the average permeability and average error percent overall. Here I've changed the data so that we have to replace maximum pressure twice and minimum pressure 4 times. So let's change this to 75, 70, and then minimum pressure, let's change it to 38 and 40. And on this one there should be an error because it's been 3 replacement attempts, and it happens, error using the program, too many replacement attempts. So in this code, the first part, this entire while loop and all these loops can be used basically for any engineering course, just in terms of having the user replace data that falls outside of a range. It can be used for pretty much anything, not only an engineering course, but any kind of course where you're inputting data and there might be human error. Second and third part are mostly confined to just petroleum engineering, this specific problem, just because Darcy's law equation and the average error and the plots are dependent pretty much on this project and petroleum engineering in general.